Good afternoon, everyone, and welcome to the UK Space Safety Engagement meetings. So we're on the first day of our short series of UK space weather and space safety engagement meetings. And we're going to start us off with Mike Hapgood from UKRI STFC's Rutherford Appleton Laboratory, who's going to be telling us a little bit about the development of the space weather reasonable worst case scenarios for the UK and the UK National Risk Assessment. As a reminder, please stay muted throughout the process. If you wish to ask a question, feel free to use the chat. If you want to come in and ask a question at our stopping points throughout the talk and the discussion session at the end, then you can find the raise hand function. It'll either be in the reactions window if you're using the latest version of Zoom, or it'll be in the participants window for the older version of Zoom. So Mike, I'm going to stop sharing my screen and hand over to you. Thank you, Mike.
Okay, thank you. I'll just share mine if I can find the right screen. All right, we're there. Well, thank you everybody for joining. As Mario said, I'm going to talk about, as the title says, development of space weather scenarios as part, which is in support of the UK National Risk Assessment. So I'll lead straight in. Some background to this. We really first having discussions with severe space weather as a candidate risk for the UK National Risk Assessment in 2010. The National Risk Assessment process actually started about 2005 with changes in the way UK handles civil contingencies. And in 2010, you may remember there was a rather interesting volcanic eruption in Iceland that caused enormous disruption, at least over European airspace. As a result of that, the government officials in Cabinet Office were looking, well, what else is out there that we don't know about? They found out afterwards that scientists had been saying about the volcanic ash risk for several years before it actually happened. And in cut a long story short, the outcome was that one of the risks identified was the severe space weather. In fact, we started around the time, I think in May 2010, a lot of informal discussions across the summer, and that led to the need to develop scenarios, worst case scenarios, to advise the UK Civil Contingency Secretariat, who are responsible for the assessment. And later in 2010, we formalized that by setting up this independent expert group that we called Space Environment Impacts Expert Group. And I didn't run fast enough and got Finger to be the chair of that group. And basically, it's a group that provides advice to the CCS and nowadays to GoScience, the Government Office for Science, I should say, Met Office and others. And as a result of those discussions, the severe space was actually added to the National Risk Register in 2011. And then various documents were published in 2012. In particular, we published a rather technical report which provided the first version of the scenarios and made them public. And the driver for getting those out was to support the document that my colleague Paul Cannon led, the Royal Academy report on the engineering impacts of severe space weather, which I'm sure many of you are aware of. Since then, we've published 2 public updates as technical reports in 2016 and most recently in, I think, July or August of last year. More importantly, also to try to actually reach out to the people around the world to explain better what we've been doing. We've now just last month published a paper in Space Weather Journal giving the scientific background to our work. So this is all these documents are published on open access with a so-called Creative Commons license that just requires attribution, and then you can read them, share them, or and even adapt them as you want if you have a need to do so. And I haven't put links to the documents in this presentation because they're available on the meeting website. So if you haven't got them and you want to see them, just follow those links. I'd also want to emphasize this talk is my summary of the scenario development. For the definitive version, and the thing that I would attribute also to all my colleagues who've been involved in this, please read the documents. Okay, the structure of the presentation. First, I want to put quite a bit of emphasis on how we built the scenarios. What are the drivers? The fact we need to understand the physics, something of the physics of how space environments actually impact engineered system. We also need to look at the kind of UK application of the impacts and not just the global issues, and also talk a bit about what we think is a reasonable worst case. Also, I want to then show you a little bit of how we structure the scenarios that focus on environments that we have to specify. And in doing all that work, I think I'd like to stress it's important that we follow the physics, but also along the way we make good use of statistics. Particularly, there are a lot of studies using extreme event methods, which give us a reasonable way of quantifying what worst cases are on, as you will see, the 100-year timescale that we look at. Later on, I'll just show you the range of scenarios that we've developed, but try to bring out something of the diversity of space weather impacts. And I'll give 2 or 3 examples of scenarios, but I don't want to go through all the cases. I think that would get very boring. Much better that you read the documents. But it's not just the different scenarios for different impacts. At some point, we then at the end need to bring them together, because space weather is an ensemble of many different effects, and the timeline at which those effects manifest at Earth will be dictated by what's happening on the sun. And it's that pattern of solar activity is where we really need to think about the sun. And right at the end, I want to show you the outcomes of where we are with this work, but also look to a bit to the future in terms of where is technological innovation taking us. Okay. Right, how we built the scenarios. There are really 3 drivers and 1 output I want us to suggest, and you'll see there's this acronym RWCS, is just reasonable worst case scenarios. I also use SWX, which is often a preferred synonym for space weather. First of all, there's the physics again. What's the physical interaction with technology and people? Then the UK, reasonable worst case, and so on. So first of all, what do I mean by the physical interactions? I think that's the key thing to developing really useful scenarios about what are adverse space weather impact environments. We don't just pick some arbitrary thing that we like to measure. We actually try to think what is most relevant to the technologies that will be disrupted or to human health. So what's the physics of that? Does the physics lead to something, I've put it in commas, inverted commas, bad? That could be an induced electric field, which is the problem for the power grid, particle radiation, which is a problem for satellites, for human health. That can be injected in and cause problems? Or is it that we have a technology that actually exploits part of the environment, natural environment, such as the plasma in the ionosphere that affects radio communications, or the neutral density in the upper atmosphere, which affects satellite orbits in low Earth orbit? Is it disrupt how we're using that environment during normal operations? So our goal in having thought about that is to identify what are the parameters that characterize the environment that are important for those adverse interactions with the technology, with human health. And then discuss what do we consider extreme values that would cause these problems, both in terms of size, but most importantly, how long would we expect them to last? What would be the spatial extent of those problems? Is it the whole world, or is it an isolated region, something like that? I really want to emphasize, we've had this in a lot of discussions also with some other countries, always start with the technology when trying to define these scenarios, trace that back to the environment and then back to the sun. That's important to go in that direction to really understand what's happening. And then once you've got back to the sun, the time on the sun, of course, drives the ensemble of threats, and it's that ensemble often makes space weather more dangerous than any individual item. I'll come to more of that later. Okay, what the UK aspects, what do I mean there? Well, this is we're feeding into the UK National Risk Assessment. So our immediate focus is on the impacts that would disrupt the UK. So most obviously, that's something that might manifest over our national territory, but also very importantly, would it affect our interactions with other countries, transport links, economic interactions, things like that. Why does this matter? Well, geography influences some of the space weather impacts on the UK. First of all, because of our we're upper mid-latitude country, I would say, just a bit south of the northern auroral zone, but they're nonetheless, magnetic substorms are very important, central to the risk posed to our power grid by space weather, because when we have a big event, it's those pulses from substorms that can really create problems for the power grid. Also, because of the peculiarities of geography, we don't have any air routes from the UK that fly over the high Arctic where there are specific problems for aviation. North America has a lot of problems because of links to Asia. Yeah, the one I always quote is Dubai to Los Angeles. If you fly from Dubai to Los Angeles, you go almost exactly over the pole on the Great Circle route. We don't have routes like that. If you go over the pole from here, you just end up in the middle of the Pacific with lots of ocean. You don't really find anywhere interesting. Also for us, because we have two islands, Great Britain and Ireland, we only have what we call HVDC, is high voltage DC. Our power grids are connected through essentially 1 million volt or 500,000 volt DC power lines that run under the ocean. You can't run AC current under the ocean. So that actually limits the effect if there are the so-called geomagnetically induced currents in one power grid. If you're AC connected, it can spread into another. With these DC connections, we think they generally stop that. So England, Wales, Scotland form one grid, which is National Grid is now the system operator for that. So we have interconnections there, but not to other countries. That's a different thing. We don't get direct GIC impact, but we need to understand that better. But it's very specific to the kind of geography we have and other island nations would have. And of course, on island of Ireland, the grids north and south of the border are now integrated and operated by Aerogrid. And another obvious thing with geography is, of course, atmospheric radiant effects increase with increasing latitude. So they're higher in Scotland than, say, in the south of England. But I don't want to imply that this is a very nationally focused thing. It's within our developments. We understand our national needs, but we see that's vital where there's international cooperation because it's ultimately a global problem. Okay, reasonable worst case. I've been trying to think how to present that. I think a useful way to think about a reasonable worst case is it's an adverse event that with a significant likelihood in the human lifetime. Certainly not 100%, but 1 in 3, 1 in 4 chance it might happen in your lifetime. But it's also not so common that we naturally develop that resilience. We're pretty good at dealing with winter as a whole, the average winter, because that comes around every year and we know we've got to prepare for it. But something that happens maybe every 50 years, it's more tricky. And the typical reasonable worst case used by insurance industry and governments are often 1 in 100 years, as for instance, UK's look for flooding risks, or 1 in 200 years is often, I think, a regulatory requirement on the insurance industry that they are prepared to cope with that. But also we extend the reasonable worst case for lower probability events if they have truly catastrophic consequences. And a very sad example of that might be the big tsunami in Japan 10 years ago, which is a 1,000-year event, but look how catastrophic that was. It tells us it's important to understand 1 in 1,000-year events if they're really bad. And then there is the issue of nuclear, where there's a regulatory requirement. We really do look at low probability events, at least 1 in 10,000 years, if not more, to make sure nuclear is safe at a very high level. And in previous national risk assessments, it's certainly always been the criterion that national risk assessment will include any risk with a likelihood greater than 1 in 100,000 years. I think risks that are judged longer than that, so a 1,000,000-year risk or whatever, will be noted but not taken further. And I did find an example in a document once. If you wouldn't really need to worry about a large meteor impact coming in and damaging a major facility. That's over 1 in 100,000 you risk of that happening over the UK. All right, what do I mean by individual scenarios? Well, you've got to remember that the target audience for our work is that we're providing scientific advice to contingency teams in government. And having chatted to them, talked this through, that dialogue shows that they are worried about a number of sectors that are crucial to the functioning of the country, the economy of society, and things like that. So the electricity sector, a gas sector, things like that, transport, within transport, aviation, rail, roads, and so on. And they need concise scenarios that they can apply to specific sectors. And then they can take our scenarios and talk with the experts in that sector and say, could you cope with things? How would you cope with this if this event occurred? So we're providing advice and environments that government officials can then use to provide a degree of intellectual challenge to people in different important sectors just for the functioning of society, you say. So what we do to provide that conciseness is we agreed with them a set of tables which specifies for a particular environment that impacts an area of concern, power grid, aviation, and so on. And we published, that's what's been published through our technical reports. And I've got there's the front cover of the July 2020 version. So it's on open access on STFC's EPUB system. So please do look at that if you haven't already got a copy. It should be relatively easy to find. And there's a link from the meeting website. So within each scenario, we try, as I said before, we try to identify, we do identify the environmental risk parameters appropriate to that area of concern. So within that, we'll provide a short description of what the parameter is. The rationale for choosing that parameter is really rather important. And then, as I said before, the worst case size, duration, and spatial extent. We also provide a summary of the anticipated effects arising from the worst case, just to inform our colleagues in government, but of course they have to talk to people in industry or who operate these things to actually really get into the nitty-gritty of that. But we don't just stop there. We do try to assess the quality of the scenario we've done. How reliable is it? Where are the problems? And particularly, how have we derived it? Where's the provenance? And certainly folks in government were very stressed they would like us to root that provenance in the peer-reviewed literature, which as a scientist I was only too delighted to do. But having then done that, we also provide a summary of what might be done to improve the quality of the scenario, what new data is required, what new analyses, ideas for how things might be improved in the future. And of course, we have a space just for other notes if they're needed. And just to give you a quick example for a power grid thing, the environmental risk parameter is partly by the rate of change of magnetic field, so-called dB by dt, but also the geoelectric field, which is actually the main physical parameter that we should consider. And the reason for using is that's what drives the geomagnetic-induced currents in and out of the grid and leads to the risk of problems with transformers. So I'll come to I'll explain a bit more about that later. And then at the bottom, you can see we start to have a suggested worst case, which comes from an extreme event analysis done by Alan Thompson and the team at BGS in Edinburgh. Okay, moving on. Oh, right. So I have 3 places in this where you can ask questions if you wish to, and then questions at the end. So I don't know if anybody wants to ask any questions at this stage, or should I just move on?
So currently there are no questions in the chat, and I don't see anybody with their hands up. But I do have a sciencey physics type question, Mike, and that's why can't you run the AC currents through the between the countries and under the water? I know there's a physics reason for it.
I think it's the capacitive coupling to the surrounding medium.
Okay.
You really want to have the cables up in the air so that you're not capacitively coupling to a nearby material. You will still get some to the ground, because I've sometimes felt that standing under a power line. In fact, trying to use a telescope under a power line, but that's another story.
Yeah.
But so primarily, it's just sort of basic electromagnetic flows that I think the capacitance and the inductances in the line will really stop you from driving the current through it if it's AC.
Thanks, Mike. Okay. In the view of any hands going up, I suggest, Mike, you carry on. Thank you very much.
Okay, to say something about the range of the scenarios then. Okay, well, there's first of all the headline on what we always talk about, of course, is electricity transmission. So we're particularly worried about power grids today because we have these very long lines which can respond to the geoelectric field and accumulate quite large voltages which drive currents through the long lines. They won't damage the lines. The currents that flow in the power grid are quite GIC currents, that are a DC current that's quite relatively small compared to the actual AC current. At worst, maybe I don't know if it even gets to 10%. The problem comes when it comes to the substations and the transformers and causes problems there. But that's something where we're concerned with the environment that's driving the currents into the transformers, but we are cognizant of what happens inside the transformers, the generation of harmonics, the potential for heating, and the loss of what people call reactive power, which is the power in the inductances and capacitances of the network, as opposed to the real power, which is the power that goes through the network and actually ends up in your home or your office or your factory. But if you destroy the reactive power, then the grid will fail. Not damagingly, but it will stop working for a while. Moving on, a really big sector for us is civil aviation. It's one where there's still a lot of ongoing work. I've put that little triangle about this, what's called the pilot's mantra, which are the three key, it summarizes in three words, three key tasks the pilot has to do in priority order. First of all, aviate, make sure the plane is flying properly. Navigate, make sure you know where you are, you're not going to fly into an area where you shouldn't. And lastly, keep in contact with folks on the ground, but do it in that order. And the problem with space weather, we can interfere with all three of them. You can have radiation effects. The performance of the plane can interfere with avionics systems. Navigation, obviously there's the issue with GPS, and communication, obviously issues with both particularly with HF radio, but also potentially with satellite communications out to planes over the Atlantic or any other ocean. Satellites are quite obviously exposed to space weather. They're actually relatively robust compared to many sectors, but they are there and we do need to worry about that. And there are a whole zoo of effects that interact with satellites. I'll touch on one later and others briefly. And finally, also I've put on this slide is the rail sector, which is we're still really trying to get to grips with. But there are issues not just with the loss of electric power, but also trains might be affected if the electric power is if you get harmonics in the power supply. Most importantly, though, is the issue of the track circuits that are used to safely run trains and have been done for about 140 years now. And if you get space weather can affect the operation of those track circuits, there are a number of documented cases, but we need to understand that better. Moving on, the previous four I would have definitely called our key national or critical national infrastructures. Now I have some things that vary, partly our infrastructures, but partly also embedded systems. So satellite navigation, Galileo, GPS, and so on. GNSS is the generic term. That's clearly a big infrastructure, although it's often also so many systems now have GNSS embedded in it. So it's a bit, and of course it's a well-known problem. To locate a position on the Earth, you need a fix from 3 satellites to locate you in where you are on the Earth's surface. 4 fixes if you also want to get time. But space weather can mess up that fix, and it can also, in fact, sometimes just disrupt the signal, so you can't even get a fix from a particular satellite. Another area that's particularly vulnerable is radio communications, both high frequency radio, where you're bouncing radio signals off the ionosphere, and that can be very severely affected by space weather. In fact, it can be completely damped out, or you can just lose a whole load of frequencies that you would like to lose because the ionosphere is in the wrong state, and so on. But satellite communications is also affected by similar problems with GNSS. The ionosphere can mess up communications between satellites and the ground, particularly at the lower frequencies like the L band, which is just over a gigahertz, which is a popular frequency for, say, satellite phones and things. Lastly, there's digital systems in general. I've just shown, but that's definitely embedded, but any digital system is prone to errors from particle radiation, even down here on the ground if particles are going fast enough. Certainly a big problem for spacecraft, a very significant problem for aviation, and not very well understood how many problems they cause on the ground. The classic case there is the election in Belgium nearly 20 years ago, where they had far more votes than voters because a cosmic ray had changed the 13th bit in a counter, and that had 4,096 votes. The point I want to make also this slide is that there is a balance between infrastructure and embedded technology. And it really does, try to me at least, exemplifies the diversity of space weather inputs. And it's important to accept that diversity. Excuse me a moment, I just need to take a drink. Okay, press on. As I say, don't look for, I think the message there is don't look for simple solutions. These are quite complex problems with many facets, and you really need to get to the bottom of each facet. Okay, some examples. I want to give a couple of examples of physical impacts of space weather. The first one, of course, is the most obvious one, namely the power grid. The driving factor in the environment is that space weather generates a geoelectric field inside the surface of the Earth, as I've indicated by the red arrow, but in the picture. And that's actually induced by magnetic fluctuations coming down from space, particularly at millihertz frequencies that I've shown there, 1 to 100 millihertz. The importance of those frequencies is they can penetrate very deep into the Earth, hundreds of kilometers, and create a large induction loop, which I've shown in green. And the size of the field that will generate at the surface is determined by the subsurface conductivity. If, for instance, you have an ocean at the top of that with its high conductivity, that you'll have a small E field. If you've got a lot of resistive rocks, igneous rocks and things like that, you'll have a large electric field. And if you have a boundary between seawater and resistive rocks, then you have some interesting issues at the interface, but that's too much for today. Important point, if you then build a conducting network on top of that surface where that geoelectric field is, you will drive currents through it, which will then obey Ohm's law and Kirchhoff's law, which is the generalization of Ohm's law to a network of lines, which is, of course, what you have with a power grid. And then that will generate GICs, which can in turn put transformers out of balance, so they generate AC harmonics, and it can also cause voltage sacking, as we've called it, in the lowering of the voltage in the grid, which can ultimately, of course, drop to precipitously, and safety systems will switch the grid off, allow the engineers to recover the system. I've put that in grey because that's not an area, not our main focus, but we need to be aware of it. So what else is there? The modelling that's been done in the UK suggests that in 1 in 100-year storm, we could get 20 volts per kilometre, which is a really big, normally electric fields at the Earth's surface are less than a volt per kilometre. At 20 volts, you can see if you had a 100-kilometre line, that's going to be 2,000 volts from end to end of induced voltage. And that could drive substantial currents. But we also don't just use the electric field. There's a long history of using the rate of change in the magnetic field to characterize this environment, which I shall talk more about on the next slide. Okay, here we are. Important thing also to note about rate of change in the magnetic field, we're talking about the rate of change of the horizontal component of the field. We don't worry about the vertical one. That's because of the way it's really the field that's passing through that induction loop I showed in the previous slide. But we use that as a very convenient proxy, but we must remember it's a vector, not a scalar. So for example, in the Great Storm of 1989, this is what the H was doing. If you imagine the static field, if you can see my cursor going round and round, there's a baseline field in nanoteslas, the X and the Y, the north and east-west components. So 0 is up here. And then during the course of the storm, these are 1,000 nanos, 1,600 nanos, 800 there. This is quite a large, and there are particularly, they see the purple and the red periods, there were very large excursions with the field doing some kind of well-organized loop. So it's not just random variations of the big field. There's some interesting physics going up in the ionosphere generating these fields. And interesting there, that's when one of the UK transformers, in fact, 2 of the UK transformers tripped out about then, but particularly the one in Cornwall, quite close to this magnetometer site in Devon. But we can often find fields can occur, these things occur as very short spikes lasting a few minutes. And so we're looking for these events, and this is during the same storm in 1989. The 2 big spikes occurred about 9:45 that evening, from a magnetometer in the Scottish Borders, Estelmuir. And that's the kind of thing we're looking at. We think the worst case could be changing as much as 5,000 nanoteslas per minute. And that's what we've taken as the reasonable worst case. So that's been applied. Finally, I should say that's also when there's a transformer in East Anglia tripped out just before the big spike crossed southern Scotland. There's probably the sort of propagation time there because it's 400 kilometers from where the transformer was to where the spike was observed. Okay, so that's the kind of thing we do for the power grid. The other physical example I'll show is single event effects on spacecraft. And later I'll differentiate that from other effects. What causes single event effects is high energy ions, typically many tens of MeV up to possibly hundreds of, or even thousands of MeV. When we have a radiation storm in a solar energetic particle event, those protons and ions will flood near Earth space, and they can penetrate inside satellites and into the electronics, into the silicon devices. And what will happen then, if you've got an energetic ion passing through silicon, it generates ionization in the form of electron hole pairs within the semiconductor. It's basically the same physics as actually use silicon to detect energetic particles, but in this case, it's an adverse effect rather than the effect we're trying to exploit. If you have those ions, I should also say that before I go on, we don't consider the background SEE rates from things like the South Atlantic anomaly. That's a static thing, so we're not concerned about that as a worst case because that's essentially always there. We're worried about these big spikes when we get a solar radiation storm. What happens if you have this ionization produced that I've shown in gray, and that can certainly cause disruption of the device. The ionization can change bit flips, so-called single event upsets. It can also be seen as a signal by the device, what's called a single event transient, and both of those can cause the device to malfunction in a non-destructive way. But it can also cause damage. Sometimes these will trigger a cascade within the device, which will burn out part of the device or the whole of the device, sometimes called gate rupture and burnout. So there's a whole range of possibilities there. But to try to assess what the worst case is, we've actually looked at a range of timescales, and I'll show you that in the thing. So it's basically how many of these particles can you cope with the flux is the thrust of it. You may also see, I'm not going to go into detail today, but you also may be aware that single event effects can also arise in devices in aircraft and on the ground during these events if the radiation penetrates deep into the atmosphere. But there's extra physics at play there. The SEPs don't generally penetrate down to aircraft altitudes, let alone the ground, but they produce neutrons which can penetrate down. Neutrons can get inside the aircraft or inside a machine in the ground, get into the silicon device, and the neutron will then interact with the silicon nuclei and produce energetic ions locally, which then generate the single event effects. So again, you've got to follow the physics to fully understand what's going on. Before I go on, I also wanted to note that this is just one way in which radiation storms affect satellites. You can also have radiation damage caused inside a device. In this case, it's a different effect, as you've got the Coulomb force, the electric force acting between the particle and the nucleus, and can actually pull the nucleus out of place and damage the crystal structure of the device. Sometimes particles will just stop in a device and add electric charge there, which is called internal charging, particularly if they stop inside a dielectric like insulation or a circuit board. And there's also surface charging, where you've got a current exchange between the plasma around a spacecraft and the surface of the spacecraft. So there's a whole menagerie of effects there. This is just one of them, right? The single event effects. So for the worst cases, we considered two different things. Well, first of all, the rate, but also the time integrated rate, the fluencies. The fluxes are important because they actually drive the instantaneous occurrent rates of single event effects. And therefore, that means the likelihood of the service being provided being interrupted. Basically, if the rate of single event effects exceeds the rate at which software in the system can correct those errors, then you'll have a problem. Whereas indifference to fluencies, as I say, are a guide to the total number of problems to be expected, and therefore that's not so much the number of problems per se, but the number of problems that an operator may see in several days. So it will help satellite company operators know how many problems they're likely to face. And then we picked a various values for 100-year worst cases, and they're based there. There's a peak photon flux of so many protons per centimeter squared per second. And then over one day, you might accumulate so many. We also in the document give a 1 week maximum fluence, which don't scale linearly with time. The shorter term things are higher than you would if you extrapolate them to longer periods. And the thing I really want to stress is that these worst cases have been significantly rise since we started this work 10 years ago. That's because of the discoveries since from 2012 onwards of proxy data about historical radiation events. That's the cosmogenic isotopes like beryllium-10 that people can found embedded in tree rings and ice cores. And they've highlighted a number of historically huge radiation events. And the headline one was also this one back in 774, 775 AD. So very much we're partly influenced by the fact we have modern measurements, partly also we have a view of what the 1,000-year levels were and can interpolate between them. Just also to emphasize again, we're talking about environments. We're talking about, we can specify the effect of the solar energetic particle environment outside the magnetosphere and effectively outside geosynchronous orbit, because the geosynchronous orbit doesn't get much shielding by the magnetosphere. The shielding is closer to Earth. But if you're applying that to a specific mission, you actually or as ever, you need to look at the specifics of the mission. How much shielding is provided by the satellites and how much is actually provided by Earth's magnetosphere? And those things have to be considered. Okay, I also wanted to touch on a non-physical risk factor, which is public behavior. We are very much encouraged by government to look at this, and we have some experts within the sea to do that. It's important to assess what's the public response to a severe space weather event. Some of you will know we did a public dialogue back in 2014 about space weather, and that produced a lot of useful information, insights, and really some really good feedback from working with the general public. Very, very helpful exercise. And two things that particularly I'd highlight here, but there are many others, but the thing that really gelled with the public is a loss of electricity. Everybody realizes it's going to be a nuisance in minutes, as I say, a serious inconvenience within a very short time, and going for days without electric power is not something anybody really wants to contemplate. Electricity is, as I've heard many people say, it's the fundamental infrastructure we have, and without it today, we have problems. Another thing, though, is satellite navigation, GNSS. We might, in a severe event, we might lose it for some times and not for others. The biggest problem is probably going to be intermittent. It will come and go, which is actually worse than probably not having it. If you don't have it, at least you then can try to come up with a backup plan. If it comes and goes, it will drive you balmy. And particularly that would disrupt logistics. And I always tend to cite internet shopping. And if anything, last year has taught us anything, it's just how important that is today. It's a really important part of our national life, most nations' lives now. Of course, and then the other really important service affected by this is emergency services now generally use GNSS to dispatch vehicles and get them to where they're needed quickly. They, I think, still reasonably good at falling back to using a paper map if they have to, but that's a skill that needs to be backup skill that needs to be maintained. And the thing we wanted to highlight, you really do need good public communication of what's going on. If you don't have that, you have all these bad things can happen. First of all, you'll get the conspiracy theorists and rumor will grow. And you really need to have a good public communication of what the science is, that we understand basically what's going on and we know how to fix it. There's the issue about social cohesion. It's very clear from social scientists that if people are presented with a crisis, they will tend to come together to solve the crisis. And that will only come apart if there's impact, if something is seen to be unfair. If something is going on, somebody's not being treated fairly. And that will then start to have the opposite effect. And then there's as we all know well from a year ago, there's the issue of stockpiling, sometimes called panic buying. And then we come on to some of the more tricky ones. Millenarianism is basically ideological and religious groups that have extreme views and then can start doing crazy things. And it's often seen as, because space weather is linked to space, that can really cause quite, people will lock onto that and head off down. And there's certainly been cults in the past who've reacted to space phenomena, and it's led to them killing each other. So something to bear in mind. And lastly, I think still to me the biggest one is increased anxiety. If people don't know what's going on, anxiety will go through the roof, and that itself is a health risk. It doesn't do anybody any good to have high levels of anxiety. And if, again, as I said, the past year with the experience of COVID, I think all of those have been reinforced by the experience of the past year. Yeah, we need to think about that for space weather, not just for COVID or any other disaster. Okay, I have another break for questions if anybody's got any to ask.
So there has been some activity in the chat, Mike, and since nobody's raised their hand, I'll bring them up here. So we have the first one from Bert van den Noord. In terms of responsibilities, how divide the responsibility for aviation between the national and international, for example, ICAO, Space Weather Services, in your risk assessment?
I think the answer is we don't. What we do have the UK Civil Aviation Authority involved in as experts in SIG. So we have an interface with them, and of course Met Office are involved, who are involved in the provision of services. So we have the UK people who will interact with ICAO, and they will run that interface. So we as SIG don't need to interact with ICAO. We have the people on board who can provide that, and we will of course keep an eye on what ICAO is saying and take it on board. We'll monitor what they're feeding back and feed that into our future assessments. I'm trying to think what else to say at the moment. The big issue is that I think what we've seen for ICAO is very good. The thing that's coming out of that is the big thing coming out of that for us is the fact the need now to raise awareness of what ICAO is doing and just raise the level of, I guess, education, for lack of level of training for people in the aviation sector of what space weather can do, and therefore how to make good use of, best use of the ICAO services.
Thank you.
Yeah. Thank you, Bert. Bert also commented that in the Netherlands, for their assessments, they concentrate on 3 aspects: the economic impact, the potential number of casualties, and the societal impact. Does that differ much from what we did, Mike, with ours?
It's not very different. Traditionally, we had a 5-level system for natural hazards. The current National Risk Register, the problem is, I was mentioning this word disambiguate to you earlier, and disambiguating the malicious risk from the natural hazards is trickier in the current National Risk Register publication. Actually, they're a bit, personally I find a bit confusing. But I think the 3 levels we were certainly concerned with economic, we're concerned with societal risk, but particularly we also highlighted, and I think it's a big issue for space weather, is the psychological issues. What is the psychological impact on people? Yeah, it's important to reassure people. I should say, when we did the public dialogue on space weather in the UK, one of the big things came out of that was for the authorities to show that they're on top of this, that they know what they're doing. That's incredibly reassuring to people, and that if the authorities are seen to be on top of it, people will work with them. People will naturally self-org. Community, we distinguish between government and communities. Communities is when people come together to get organized to solve with the problem, and the important thing is for the authorities to mesh with that. Does that make any kind of sense? So the space weather, we don't expect much in the way of direct impacts on human health. But you might have indirect impacts. If infrastructures are out of operation, there is a risk of accidents leading to injury and I'm afraid to death. Classic issue there would be failure of traffic control systems. Most of us going into a road junction with the lights out would proceed cautiously, but I'm afraid some people will think, oh, the road's clear, I can go through at high speed.
Yeah, that's a good point. And that actually comes to a related question that Siegfried Gonzi asked, and that's, has there ever been a recording of somebody just died because of a space weather event?
It was raised once in the United States. One thing where somebody might die is if somebody decides to use smart munitions in a warish situation and there's a space weather event at the same time, so that the navigation systems are out. I'm happy to say that because it was in a public meeting in the US. Other things, well, historically, of course, we've had back in the days of telephones and telegraphs, we had fires that got out of hand. Fortunately, I don't think anybody was injured in those, but there have been a few near misses. Oh, another example from the States. I don't know details, but pointing the point, somebody took a wrong turning because of satellite navigation playing up, which could of course occur during a space weather event, and they got their car stuck on a railway train, and the driver got herself, I think, and her children out of the car before the train arrived. So they didn't get killed, but I think the car wasn't in good shape. That's the tale I've heard anyway, and it sounds plausible. We know in the UK there are lots of problems with people, GNSS sending people off wrong roads, trying to cross a foot ferry with a car, or going down roads that are just too narrow for their vehicles. So,
thank you, Mike. There's been a few comments in the chat regarding the military incident that you mentioned, but in the meantime, Bob Bentley, you have your hand up. Would you like to come in, Bob, please?
Yeah, it was a couple of points. Was one, you mentioned the fact we don't have any transpolar flights and therefore don't suffer the HF comms problems that North American routes do. But we do have a lot of flights that go at quite high latitudes, and so other effects like radiation and that sort of thing come into play.
Oh yeah.
The risk registry often concentrates on things that are affecting the UK, but of course this affects UK industry. Our airlines, and I just wondered if that's properly covered in the.
I believe so. I think, for instance, the classic one we think of is Heathrow to Los Angeles, where you quite happily will be going up to above 70 degrees.
Yeah.
So you would certainly wonder where you'll be worried about radiation effects, loss of HF comms, possibly, but the big thing about as long as you're equated with 82 degrees, you should have SATCOM as a backup for communications. The magic thing is that if you go north of 82 degrees latitude, you can't see the equatorial satellites, so you can't use SATCOM via an equatorial satellite. You maybe use some of these new constellations, you may have a signal, but if you don't have communications, you're not allowed to enter that airspace north of 82 degrees north. So that's why the control center, I think, is in Edmonton in Canada, and they will, if there's say a big polar cap absorption event due to a radiation storm, they will close the polar airspace and people have to fly a long way around.
But you've also got, for instance, if you look at the route from London to Tokyo, the frequent flyers, in particular the dedicated air crew who are there because of their language skills, they get up to the allowed radiation limit.
Well, the frequent flyers, I'm afraid, are on their own. The law does not yet cover them. Well, at least nobody's tested it in court. For their crew, there are new air navigational regulations came in 2019. So they are monitored, and I can't remember, what is it, if somebody has to be classified if their exposure exceeds some level, so then the airlines have to try and stop it exceeding 6 millisieverts in a year or something like that.
Yeah.
I can't remember the details, but as far as I know, there are new regulations, but I don't believe there is a code of practice yet for that. And that would
I think the UK is now transferred onto the ICAO rules, hasn't it? Because it was under Euratom.
Yeah, but we need for us scientists to get involved, we really want them to produce a code of practice. So that's something we can understand. When you have a bunch of scientists trying to look at legal regulations, it's the legal spaghetti is confusing, shall we say.
Yeah, okay. And the other point was, are you going to cover the mitigation of various space weather effects?
Not in this talk. We may allude to it, but since the scenarios are there to drive everybody to what is the risk and then set the mitigation process in train. So I'll end by talking about showing the current risk matrix, and that, of course, what we do to help government, to advise government so they generate that, that's the driver then for the different sectors to do mitigation.
Okay.
So there's a kind of chain of events, and mitigation isn't really in scope of what I'm talking about today. But yeah, it's there, and it's certainly interesting. And
well, it is interesting if you have situations where it's hard to do the mitigation.
Sorry, just taking a drink. Yeah. And that's where you have to understand the environment. What can you do about it? But you can easily, obviously, the easiest way to mitigate in an aircraft flight is to stay on the ground. But
these events can take, it can be 13 hours long, and an event can nothing happening to being quite severe during a 13-hour flight.
Yeah, but there you've got the issue. Is it, do you want to land because of the risk from radiation, or is changing course more dangerous? Is that the greater risk? So there's a balance of risk issues.
I mean, I think the dust cloud of a few years ago and 9/11 demonstrates how difficult it is for aircraft to suddenly change their plans.
Yes. Yes, it's a potentially very dangerous thing to do. So it's something, if we talk to, when we talk to pilots, that's very much something, ground that they would want to think about, particularly if they were also to lose comms at the same time.
Yes, because you do run that risk.
Yes.
Thanks, Bob. Clive, I think you were next with your hand up.
Yeah, a lot of it's been covered, but I just want to dip in there. You've got to realise your London LA or London Tokyo flights in the Feb 56 event within an hour would exceed the annual recommended limit of 6 millisieverts. You go up to the 100, 150 year event, you will get more like 27 millisieverts. I don't think anybody would be very happy. At the same time, all your comms and navigation would probably go at the same time. And in terms of mitigation, if you're in mid-flight, what do you do to mitigate? It's all very well getting warnings getting early on, staying on the ground, but you're going to be landed with a very severe problem, a lot of lack of pilot awareness, situational awareness, knowing what's going on if there's no comms and it's been irradiated.
That's the interesting issue, was the question that Bert raised earlier. The big issue now is we have a lot of bits and pieces there in terms of the ICAO services and guidelines and things, but there's a need, as Bryn, I'm not sure if Bryn's on this call, but as Bryn has often stressed, the need now is to raise awareness of that. So there's a kind of big education issue.
Yeah, awareness is one thing, but not knowledge at the time is another. That's what we must provide people, and I don't think we quite have that at the moment.
Yeah, there's plenty. Well, when we come to my final slide, yes, it is on the final. You'll see that that's an area where that aviation is one of the areas I think where's continuing work needed.
Thank you, Clive. Mike, Clive did make an interesting comment as well, which he didn't mention, and that's that we've only had some 60 years of advanced technology, and that we haven't really had a severe space weather event in over 100. So I think he's making the point that a lot of modern technology still hasn't been fully tested with severe space weather. I think that's a good point to make. That
it is a very good point to make. Yes, I'll even allude to that bit of that particularly from a personal point of view in one of the later slides.
Okay, that's good. Edmund, I'll bring you in here, please. Edmund Henley.
Thanks. Just very quickly, Mike, was just wondering, given you was pointing out the COVID experience, given that, a lot of the National Risk Register has driven tabletop exercises, practicing things with the community, and that in some ways, I know that the the downstream impacts of a space weather event might differ in some ways from the in many ways from the COVID ones, but I guess there will be some common elements. And I was wondering to what extent there's been reviews or planned reviews of kind of the assumptions built into those tabletop exercises. Mario says that there's some, I had said in the chat that there's some planned reviews, but I was wondering if you could expand on that.
I think it's something that we need to get on with, basically. I don't have, we haven't done much on this in terms of this. I think Met Office, some of your colleagues have been involved in sectoral exercises in recent years, but it's high time we did some more exercises at both national and regional level. I know in the past we've done a number of national tabletop exercises, and also there was a regional thing done in Stafford a few years ago. So, but part of that is to really bring in not just the kind of national teams in the ministries in Whitehall, but also bring in the local civil contingencies officers who run the regional, what do you call them, local resilience forums, get the correct term. And the local resilience forums are something that is not perhaps as well known as they should be. The fact that there are these forums so that people, the key services at the local levels, the councils, the police, other emergency services, and probably some of the voluntary sector, they can get together and actually try to understand what the risks are for their area and then be ready to act at a local level. And some of that, then there's all this business of bronze, silver, and gold commands, depending on where you are. And I guess if you had an emergency, your local commander would be bronze and so on. Then. But there is quite a sophisticated structure in the UK built up since 2004 for dealing with emergencies. And you've seen some of that in the complexity of how the COVID stage has developed. That's because it's gone on for what seems like forever. There's a complex structure built up to deal with all the different facets. A space weather emergency would just probably last a few days, and it would be a very different kettle of fish. But we'd still be trying to work within that same framework of government trying to pull things together to deal with the emergency. And
Simon, you wanted to come in there, I believe. Simon Matchin.
Yeah, I was just actually typing something up there, but yeah, I may as well say, just to add to Mike's comments there was a little bit of, there has been some work done looking at concurrency of COVID recovery alongside space weather risks, as there was with a whole host of other risks, to help understand where the COVID recovery phase might act to either increase or decrease, indeed, risks associated with various phenomena that are already within the National Risk Register. So there was some work done around that, and with respect to space weather, I mean, one of the interesting ones, which Mike has already alluded to in his talk, was around financial transactions, internet, and the fact that potentially a space weather event could actually deny access to electronic transactions, and thereby drive people more towards a cash society, which is an increasing contrast to the effect of COVID. There are other things where, obviously with transport, if there are fewer flights, then the impact of space weather might be somewhat less than anticipated under normal conditions. But as I say, there has been some work done around that, but I think as with much of this, there's a great deal more to do.
Okay, shall we move on?
Mike, so we have a couple of questions that came in directly to me. They may or may not wish to be anonymous. I'm going to treat them as anonymous. The first one is, what can you explain about the reactive power on the grid? Is this something unique to the UK grid, or is this something which occurs across all power grids?
It occurs across all power grids. Every power grid, no power grid is purely resistive. As I think it was Trevor Gaunt, who's one of the South African experts, a real expert in this area, much better than me. You may point, the current and voltage in the power grid are not in phase. And that indicates the fact there are reactive elements in the grid, so inductances and capacitances. And it's the power I always visualize it as the power in that part of in that phase that's out of phase with the so-called real power, as engineers call it, which is actually the power delivered to you to do something useful. It's power that's needed to run the grid, but doesn't actually get delivered to our houses. If that's not there, it's not working. And if you look at I think National Grid, well, certainly many grid operators have specific contracts to make sure that they've got the reactive power. If you read what they write about things, one of the things that they would do to prepare is make sure that they're ready to put reactive power into the grid. Because I think when the transformers start playing up, that will cause loss. That causes loss of this power. So it's critical to grid stability, shall we say?
Thanks, Mike. And there was one other that came in privately, and that was, has the impacts of space weather on the water industry, so talking particularly about the remote control systems, been analysed at all during the current feasible worst case scenarios?
I know that there was a NERC-funded study which involved possibly Atkins and MSSL. I think in the past we've tended to cover that primarily in terms of in the reasonable worst case scenario, it's covered as part of the impact on terrestrial electronics. So it's the fact that a lot of infrastructures use a thing called SCADA, which is an acronym whose name I can't remember what all the words mean off the top of my head. But it's basically the electronic control systems that control so much infrastructure, and allow that so that the operators can sit in a control somewhere rather than these companies having to have lots of people charging around manually operating infrastructure. And so the concern is that if you had a really intense ground level enhancement, could some of those infrastructures be disrupted, not just by loss of power, but also because could you have problems with the electronics, single event effects, causing certainly at least disruption, hopefully not damage, but you can't be sure of that. And so I think that's the thing. It's a generic thing to all infrastructures. Same would probably would apply to gas, for instance. As well as water. At least that's my understanding. Bob
has his hand up. He may want to come in with something more here. Bob Bentley.
Yeah, it's about concurrent disaster, concurrent events again. Since this has been brought up, when you have a power grid which is subject to a GIC, then you open everything up in order to protect everything, so the current can dissipate. But if it happened at the same time as when you had a very severe storm, terrestrial weather storm, high winds, then you're probably starting to close the grid down to stop power cables crashing against each other and shorting and things like that.
I don't know that they do that.
I think you do.
Certainly National Grid, I've always been told National Grid, if they have a certain terrestrial weather storm, they will certainly position teams ready to where their lines are most vulnerable.
But you see what point I'm making? If
absolutely
you are doing these two things, they're diametrically opposite to each other.
It's the same as COVID and space weather about how you pay for things, isn't it? Cash versus cashless transactions. So yeah, that's something that needs to be fed into government for them to try to draw that thing. It's not for us because we don't want to. We shouldn't. Met Office can do this because they have both expertise. It's here am I exporting this onto Simon and Mark and things, but
it's that the analysis that goes to government should mention things that occur to us where ability to mitigate something may be affected by another event.
Oh yeah. I'm not sure what to say other than that.
Yes.
In the sense, we're delivering we're trying to tell what the worst case space weather is, but the fact that bad space weather can occur in conjunction with something else is a big concern. Yeah.
Yeah. Well, whether it'll occur to the government is another question.
It will certainly occur to the civil servants.
Yeah.
Thank you, Bob. One last bit before we move on, actually, is from Bert again. And this is pertinent because he asks about, does it make sense to distinguish between the mitigation and the adaptation to space weather?
I'm
So
not quite
they're two
sure what
different
the
things.
distinction is meant there. I think I would regard both mitigation as generically, whether you're trying to build something in resilience into the engineering, or whether you're making some adjustment to the system in response to a forecast. The thing I always think of it is if when somebody builds a system, the first thing they will do is try the engineering mitigation if it's not too costly, and so that what the adaptation in response to forecasts, if that's what's intended, where that comes in is where you can't do, or it's too expensive to do the engineering mitigation. So it's always important to understand the engineering defines the space in which forecasts are useful. So for instance, in the power grid is particularly a system that's open to adaptation, as Bob was just saying about, you know, the part of the idea is to try and cancel maintenance and make sure we have everything on to dissipate GIC, also to have all the reserves ready to supply this reactive power if there are problems with the grid. So that's the classic case of that. It's a balance. There's no simple, as usual, there's no simple answer. Part of it, a lot will come down to what's the I wouldn't say cost, the cost loss issue, and cost, not just cost benefit, but there's been quite a bit of work coming out of meteorology, but also now applied to space weather, looking at cost loss studies of how valuable forecasts are to particular users.
Thanks, Mike. Bert, you've raised your hand if you want to come in.
Well, yes, I think that in a way that I consider normally where, for example, when there's a space weather alert, then sectors will make their mitigation measures. But the adaptation is something which I discussed at some time with the power grids. They said, well, in the future, because there will be more local energy generation by wind parks, etc., the topology will change, and that is basically an adaptation which makes us more resilient to space weather effect. So the network topology will change, and that is considered adaptation. And I see. Do this distinction in this way. Thank you.
Okay, I shall come back to that at the end of the talk, actually. So
okay.
That's useful.
Thank you.
Thank you very much. Thank you, everyone. I have some questions in the bank for later on, but Mike, I think I'm going to use chair's prerogative and allow you to carry on with the talk, please.
Okay. Right, I've talked about so far about the individual scenarios, the individual risks, but it's important to bring them together to recognize space weather as an ensemble of risks. You know, we were talking just now, Bob was saying about, you know, you could have bad space weather occur at the same time as bad terrestrial weather. That's certainly true. But also we have so many different facets of space weather. They can happen in some time sequence, which may vary from case to case. And I think one of the things that's really been important for governments in seeing space weather as a serious risk is the fact that many things can go wrong at more or less the same time. So please don't try and understand the entire tree. I just want to present this as a tool we've used in talking with people in government. We called it an impact tree. So at the top, we start with the sun, the effects such as coronal mass ejections, or SEP events, high-speed solar wind streams, and then trace down to what is the environmental effect that then occurs at the Earth, what effects are then interfering with technology, and what are the systems that are then impacted. There's also at the bottom, just to emphasize, to be inclusive, we note that there are some sources of space weather effects that don't come from the sun, particularly convective weather systems in the troposphere can affect the ionosphere by sending atmospheric gravity waves up and disturbing it. It's quite vertical coupling, as it's sometimes called. Also, the convective weather systems can also spawn thunderclouds, and they can fire off gamma rays and hence positrons, certainly fire gamma rays upwards, which is an interesting issue in terms of effects on spacecraft. Not very well demonstrated, but certainly theoretically, and there's certainly a book I was involved in where one of the other chapters was try to look at that. And we mustn't forget, of course, that we also have galactic cosmic rays that vary a bit over the solar cycle and according and where the CMEs pass us, and probably more generally over the millennia. And of course, those all come from shock waves in supernovae. Don't forget the supernovae matter in that sense. So this we found is a very useful way of showing the complexity of space weather and some of the interrelationships, and certainly it's been much appreciated by some of the people we've worked with in government, and we developed the original format together. So I just offer that as one way of looking at the diversity of effects and impacts. But another thing to consider is typically, I think, but historically, most severe space weather events tend to occur. We've got 1 or 2 weeks of, dare I say, chaos. And the 2 weeks is typically set because we have an active region on the earthward side of the sun and it's rotating from east to west. That's why it's 1 to 2 weeks. The events in September 2017 were a good example of that. But the big storm in 1989 was like that. The May 1921 event was like that. And Carrington's event in 1859 was like that. We certainly know of those. During that period, we'll get multiple CMEs and SEP events occurring. I'm trying to remember how, but I remember after the end of the 1989 event, there was just some enormous number of flares that popped off as well, let alone CMEs and SEPs. And you can get things like, I always like to quote this example as the diagram on the right, which I came across a few years ago. The big storm in November 1960, which has not really been as well studied as it deserves. But there we have this double whammy effect, as people speculated could happen, but it's a real example where we have a coronal mass ejection arriving at Earth just at the same time as a SEP pops off on the sun. So this is the DST index. Here's the sudden impulse at the start of a magnetic storm, the enhanced field, and then the big drop down in DST to the main phase of the storm, and then a recovery, another little storm here on this date here, if you can see where my cursor is wobbling about. But looking back in the records, it's the CME that caused this event probably launched from the sun about here. Obviously, being 1960, it wasn't observed, and in fact, no flare was observed that day because we have the solar flare patrol records, which show there was no coverage at that time. But we do know from other records that there was an enormous radio blackout in East Asia at that time, and suggesting, of course, that there was an enormous flare, and so it's likely the CME launched at that time. 36 arriving at Earth 36 hours later, giving the sudden storm commencement. But that event at the top, there are the cosmic ray accounts from 2 sites, one Climax in the Rocky Mountains in Colorado, and one Antarctic Station Mawson, both showing these big events, and it occurs within the sudden storm commencement, I think, was like 25 minutes after the start of the flare was observed associated with that SEP event. So that's basically 2 separate events on the sun produced simultaneous effects on the Earth. And there is concern always is if we have a big SEP event going on, leaving the sun just when a big CME arrives at Earth, the magnetic storm may reduce the shielding that's provided by the magnetosphere. So the effect on the atmosphere will be greater. This actually effect isn't so bad. It would be far worse if the SEP event had started during the middle of the main phase here, when the magnetic shielding was probably most reduced. But it's a really good example. The sun can send 2 nasty things at the same time. And those 2 nasty things are typically the geomagnetic storms, and that can produce the GICs in the power grid, but also can disrupt many kinds of radio systems. It certainly can increase satellite drag, so we don't know where lots of satellites are, and can also change the plasma environment, so we get more extreme charging of spacecraft particularly in the higher orbits. But at the same time, you can have the radiation storm that causes single event effects, satellites and planes, as I've discussed before. We also get the satellite radiation damage, radiation doses for aircrew and air passengers, as we talked about, and also that can produce a HF blackout in polar regions, hence affecting transpolar flights. So we have all these things can happen at once, and that's one of the challenges of dealing with a space weather event, and why we have all these scenarios to advise different sectors. But the advice to government is also, you're going to have to deal with all these things at the same time. And that's, I think, the bigger challenge. If you've got problems occurring like that, and it's important to know that they're related. It's also important, of course, to know that where things are not related. Back in 2017, you may remember Mexico had a big earthquake about the same time as the space weather event. And our colleagues there were having to brief their government, I think right up to the president of Mexico, that these things were separate, because they had the press and conspiracy theorists, of course, trying to link the things together. So, yeah, an example where public communication is also important. Here's a simulated timeline. It's taken from the Royal Academy of Engineering report, but simplified to make so I can present it in under an hour. In this simulated event, we have a fast CME being launched in our direction on 20th of March. It doesn't matter the year. I've just picked spring equinox because that's one of the times we would have the the biggest effect on the Earth from a CME. But the CME shockwave in front of that fast CME will generate energetic particles, and they, in this scenario, they reach Earth very quickly. So we have this CME launch here on the left, but this big, huge blob of red energetic particles coming down all this time of a day or more. Then we would have a persistent radiation storm, and it would continue because as the CME travels towards the Earth, so it pushes the shock in front of it, and that will keep firing particles at us. I've taken a Carrington-like type event so that with the CME is taking 17 hours to reach the Earth, and we get a geomagnetic storm starting here, this column geomagnetic activity. But the magnetic storm will manifest as a series of pulses, what we call substorms. So the Earth's magnetosphere stores energy for a while and then releases it potentially in a big pulse, and it's those big pulses that often produce some of the effects on the power grid. So the substorms are an important issue to remember. And when we're talking to government, they're really appreciative of the idea that you could have a pulse of activity that could threaten the power grid, and it could go quiet, but it could come back. So don't say we're all clear after the first substorm. There could be another one happens, and in fact, that's really did happen in 1989. There were 2 big substorms over the UK. And lastly, though, assuming there's a solar flare associated with the CME launch, which is quite likely, that would cause a HF blackout. But because in this plot, it's occurring simultaneous with the launch around midnight universal time, UK would not be affected because it would be nighttime here, and we're not affected by flare. Flares only affect the daytime, day side of the Earth. So it just gives you an idea. We would have a sequence of all these events, and some effects coming from the radiation storm, other effects coming from the geomagnetic storm. Say the pulses from the substorms would certainly be the problem for the grid in the UK, but that series of pulses would also build up effects in the atmosphere, gradually increasing satellite drag. So that's much more of an integrated effect from the storm. So after that, we would probably have some changes, in significant issues with satellites not being where simple models might forecast them. So the people who track satellites would have a big job to recover them all. Could take 2 or 3 days to just know where everything is in nearer space again. I was also going to have a last intermediate break for questions, but maybe I should press on to the end. But if there's a pile of questions, I can answer them now.
There is one question that's pertinent probably roughly at this point, Mike. And again, it comes from Bert. Financial sector in the Netherlands was very concerned about the loss of GNSS. Does the UK have a similar concern?
It certainly did, as I was looking at that earlier. But there was a big workshop in London looking at this in the summer of 2014. And I think certainly at that era, there was a lot of work done with that. And, you know, I had the impression that at least the UK financial sector had begun to get to grips with that, because out of that work in that era, the National Physical Laboratory has developed a service which is up and running now to provide accurate timing to the city via landlines. So you don't need to use GNSS. And of course, there's a certain cost with that, but we generally have the feeling that the financial services sector can afford that kind of thing if it's critical to their operation. But I'm not entirely sure what the take-up is on that. I really don't know, and I certainly don't know if it's applied to any other services, as you say, in Netherlands or Frankfurt, Paris, let alone New York. It's a good question.
This is Bert. I only want to say the problem came about because national atomic clocks were stopped as being too expensive, and they were now considering time code via internet.
That's what was essentially provided in UK,
Yeah.
but it's based on an atomic clock, obviously in a national lab.
Yeah, it must be somewhere indeed. But
Yes, it's in the west of London at Teddington. That's where the National Physical Lab is. But
it's a point to keep in mind. Sorry, thank you.
yeah, it's no problem. But we're just relying on GNSS timing is, to me, is crazy. For reasons I'll come more to in the past. But when we did the original studies, particularly for the Royal Academy of Engineering report, it's all written there, so it's all public. But one thing we did that was checked there was, to what extent do our mobile networks rely on GNSS timing? And the answer was the commercial networks didn't, which was great news. And they use essentially have presumably atomic clocks, and then they use network protocols to exchange time and synchronize. And there are ways and means of doing that. And don't ask me, I'm not an expert, but I do know they do it.
Perhaps you can help the Netherlands. Thank you.
Thank you, Bert.
Okay, I'll send you a link to where the MPL service is Bert.
Clive Dyer, you want to come in?
Yeah, I want to come in with a comment, really. I echo what Mike said about these sequences of events being so important. 1960 is a very interesting example. We do have some smaller examples where we got real data. For example, October 1989, a whole sequence of events affecting spacecraft and aircraft. The 24th of October was the ground level enhancement, not a particularly large damaging one, but we did detect it on Concorde. And it was some 50% higher than it would have been in an unperturbed geomagnetic field. It was a near KP4 at the time, but that was enough to increase the dose levels and radiation levels of the aircraft by 50%. That's something we're trying to take account of our models under the SWIMMER project, which is being publicized tomorrow. It's so important to remember that you don't necessarily have geomagnetic shielding in the way you think you're going to get it. That could be a real problem in a major geomagnetic storm. There's a sort of myth in aviation that if you're below 45 degrees latitude, no matter whether it's geographic or geomagnetic, you're safe from solar particles. Well, you're not if you've got a geomagnetic storm in hand.
I can only agree. You have some nice data from '89. I think it's really useful.
Yeah. It's something we've gone and studied some more in SWARM. We'll maybe take a look at your 1960 and see what that would have done. Of course, we don't have the measurements of the aviation radiation, but we'll say what if.
But there is quite an extensive network of cosmic ray monitors, and I think all the data is at the Cosmic Ray Data Center in Japan. Quite easy to access.
Yeah, we can get the neutron monitors, etc. Just say there was nothing in the air.
There is one related comment coming back to NPL, Mike, and that's from Jackie Wood. And there's actually SPF, so Strategic Priorities Fund program, project funded on the resilience of time standards to address the sorts of resilience issues that's being discussed here, as well as other timing resilience issues. So that's, of course, the same funding program as what SWIMMER is funded from, for those that know about the SWIMMER program.
That's very interesting. Oh, well, yes.
And that came from Jackie.
Thank you very much, Jackie.
Yeah. And P.S. Jiggins also pointed out that if we're looking at timelines, the October 1989 event that followed the September 1989 SEP events, they all came from the same active region, and that meant there was a period of well over a month of sort of ongoing activity there. So I guess that harks back a little bit to your yes, shortened timeline of events that you showed, Mike.
Yeah. We've used those events in some socioeconomic studies. And I did also discover recently there is also an event in July, I think, of 1959, whereas the SEP went. It was the longest known SEP event in terms of its effect on the polar ionosphere.
Thanks, Mike. And there's one more private comment that came in, so I'm going to treat it as anonymous, and that is, how much do differential GNSS techniques mitigate for space weather effects?
It's going to depend. By differential, I guess they mean that the ground-based systems used, for instance, either for accurate surveying or getting ships into ports and things like that. I think It's there. Should help a lot in terms of correcting for the TI, for the effects on total electron content, because that then they're constantly measuring that. Same would be true of the augmentation systems, which I tend to sort of lump in a bit the same. The satellite augmentations like EGNOS. Where they won't augment is particularly if you've got strong scintillation, because you could just lose the signal and then it'll stop working.
Thanks, Mike. I think if you want to continue, we'll come back with a few more questions at the end.
Okay, right. So, and finally, as I said, so this is the last stretch, outcomes and thoughts for the future. So the outcome is really quite simple. It's just one slide. I've finally brought myself down to there's a new national risk assessment published in December 20 of last year. So I've now finally sat down and extracted from that and put it in a format that's better to present. And I focused on that, just on the environmental hazards, which of course space weather is one, and on health hazards, because that allows me to put pandemics in the plot to give you a reference point. But the wider assessment includes accidents and malicious events. So that's people that, it's criminals, rogue states, terrorists, people, things like that, which I think A, you wouldn't better read the slide because there'd be so much stuff on it, and B, it's a bit out of our range. Whereas I think health is reasonable to compare. So the risk, it's a kind of standard risk matrix in that we've got probabilities going from left to right at the bottom, and also then going up the top. The new restoration calls them A, B, C, D, and E. I've used the old terms also to the word terms for them. I'm not sure how appropriate they are for the new register. I haven't managed to dig into it enough yet to do that, but I guess that's probably useful, certainly useful. And the probabilities are now expressed in probability in the next year. Now an important, two important things to say here. The impact scale is logarithmic, so it's not just the catastrophic is 5 times, it's more like 10,000 times worse, shall we say, something like that. Now, the position of risks in this matrix, the government does this on the basis of expert advice. So we are providing the expert advice in terms of space weather scenarios. We don't locate things in this matrix. We really provide the advice, and then somebody goes away and does that. So you can see where space weather is in good company with things like poor air quality, surface water flooding. It's a risk that's judged to be worse than 1 in 100 years and less than 1 in 20 years. So we have earthquakes, of course, occurring in the UK at a similar level, but much less. In UK, earthquakes are not generally very dangerous, thank goodness. But the higher risks in that similar category, you've got pandemics at the top quite naturally, and then the big risk in the UK often is the flooding. So we have plenty of water, both in the sea and in the rivers, and can cause all sorts of problems. More frequent risk, then we've got a lot of weather ones, volcanic eruptions, and not unsurprisingly, an environmental disaster somewhere in the world is going to be more probable than one in the UK, because we only occupy 1/2000th of the Earth's surface. So that's really where we are. The key thing to note about this risk matrix is that the position of risk here guides the investment, what the government really feels it should be investing. So the closer you are to the top right-hand corner, then the more important the risk, and the closer you are to the bottom left-hand corner, the less important it is. And you'll see that actually there are the two leftmost and rightmost columns are empty, because they, in the full risk matrix, they contain malicious events and accidents, but there are none of these environmental hazards and health in those categories. What else to say about this? So you can see that severe space weather has long been rated as a serious risk, and still is something that's taken quite seriously. And that sort of drives various activities. This is the ultimate driver for the government in thinking on these, and risks are then shared out across government. So within the UK, the Department for, let me get this, risk, business enterprise and industrial strategy, so-called BEIS, is now the lead department for space weather. So we work closely with them. Government Office of Science, of course, looks at all of these and coordinates scientific advice. And Met Office is assigned to be the risk owner for this. So they do a lot of leadership work. And again, they're very much involved in this activity. Right. Okay. That's why all I want to say about outcomes. The fact that the outcome of this process is that risk matrix, and then that can drive things like mitigation that we've talked about in some of the questions, and that's downstream from this. But more, where does our assessment work go in the future? And the key thing I want to make here is that what lies behind all our concerns with space is technological innovation. It's a central feature of modern societies. It's been it's been important for at least the last 300 years since the start of the Industrial Revolution. And I'm sure some historians could argue earlier than that. It's also very much a feature of our economy over those 300 years. Innovation is really important driver of economics. And what comes out of that, the big plus, of course, is the vast improvements in human well-being. So having set that context, pointing out it's space weather, it's technological innovation that has created the vulnerabilities to space weather. There weren't any space weather vulnerabilities in medieval times. Obviously, we didn't have the technologies. But then from the middle of the 19th century through into the middle of the 20th century, we started to have impacts, but in technologies that then didn't really have big impacts on everyday life. Yeah, they started to affect the electric telegraph. The first recorded problem was 1847. There's a very good report, I think, in Nature about phone problems in 1894. HF radio, high frequency radio, started to develop in the mid 1920s. The early stuff with Marconi wasn't HF, but there's papers in 1928, one of which is actually by Marconi, and then where these people start to catalogue the problems that space weather causes. And the first recorded incident with a power grid is 1940. But in all that era, these are technologies that don't affect too much of everyday life. They're much more specialist thing about for governments to worry about, for commercial companies that have to coordinate over large distances. In 1940, most people only needed electricity for lighting. But things have changed since, say, 1960. Say in 1960, we had a world where coal was still king. Coal was a big source of power at homes, offices, and factories. Most communication was paper mail. I can say that confidently because that's the world I grew up in as a kid. Since that time, electricity has become dominant. We really need electricity to run our homes, to run our offices, run our factories. And as the last year has brought home, even though we knew it well before, electronic communications is the dominant thing now, not paper mail, and there are many other things. So, and that's really why, since say about 1960, space weather has become such an important risk issue. But the important thing to look to the future is that innovation is going to continue. There's no avoiding that, and so will new space weather risks start to emerge from that. But also, some space weather risks may disappear. Technologies may eliminate them. The classic one that has happened is the way in which optical fiber has really removed the big space weather risk to landline communications. Up until the 1970s, there were huge problems with landline communications, telephones, telegraph from space weather, and that's gone away because we now have optical fiber, which still needs power, but you don't have you can't run GIC down a piece of glass, basically. Okay, so some of the technology, first of all, two last slides, some of the technologies that we need to look at for the future. The big one is autonomous navigation. Not surprising. It's not all GNSS, but GNSS is part of the thing, and so space weather has to be a factor there. My impression from a few conversations is people working on this are well aware, and they are trying to they will use a fusion of technologies that really reduces the space weather risk. But we have most obviously autonomous navigation for driverless cars. We also have aircraft, and I did manage to find a drone that did something useful. In this case, it's for carrying medical supplies, and from a UK context, they were actually using it last year to ferry medical supplies out to the Isle of Wight during when COVID kicked off and the ferries were reduced. And certainly in Norway, I know there's already a lot of work going on autonomous shipping. Fortunately, they can do their first test in a nice, well-charted fjord with almost zero tides, but it's a start. And so those are things that certainly need to be watched. And how are they resilient to space weather? Another thing, as we touched on a bit earlier, I think Bert mentioned this in time, is green power. Here's a nice solar power station in the west of Oxfordshire. and there's a few wind turbines in the background. Big thing about green power is it may be more local, but also one of the big things that the power grids are working hard on is that it reduces the amount of inertia in the system. Power engineers will talk about a thing they call spinning mass. And in conventional power generation, that's the inertia in the big steam turbines, whether they're in coal power stations or in nuclear power stations or whatever. And that produces that's got affects the time constant of the grid. That means that the grid takes tens of seconds to change. And now you're moving to solar arrays don't provide inertia. So things like battery farms are being developed to be able to react within a second. And that's certainly happened in some instances in the UK. We do need sort of basically big farms of lithium batteries to cope with things suddenly dropping out. Now, whether there's a space weather effect there, I don't know. It's just something that needs to be looked at. I just flagged that as a way a key vulnerable technology is changing, and we would like to understand better. Is there an issue there for space weather? Right, it doesn't need a big logo. 5G. In the UK, the Royal Academy of Engineering Assessment spent a lot of time looking at 4G mobile comms. I'm not aware of anything that's got into depth about 5G. Personally, just looking at it naively as a scientist, it might be more resilient for two reasons. One is I think the synchronization requirements for 5G are more demanding, and with a bit of luck, and I've put it that way, GNSS timing may be too bad, too crappy to actually be useful for 5G. You need better timing solutions. And the other thing is because 5G has this idea that it will do beamforming so that it will try and track where your phone is and make sure you've got a focus signal on you, that may reduce the issue about interference from the sun, which could also interfere with mobile phone operations. Right, last on this side, which Simon has also mentioned, is cashless payments. You know, cashless payments have been growing for years. There is, I think I've cited it in some publications. There is an article published in 2012 where somebody, a Norwegian guy working in New York, Espen Haig, published a nice article on the risk of events such as space weather wiping out our electronic transactions. When the gods destroy our money, I think it is called. And there's an interesting issue there. You know, we probably need cash and cashless to have resilience. Certainly that's been my experience during COVID too, that suddenly on many occasions now I've been trying to pay for something and their card machine's has been bust, but I've always had some cash as well. So something to watch. Okay, those are technologies that are really coming in and really haven't been evaluated for space weather, at least as far as I know. Somebody may have done so, but I'm not aware of it. But also there are things that we're still already studying that we probably need to keep an eye on. And as we had some discussion, I think, with Clive earlier, civil aviation, there's plenty of work to do to get fully on top of civil aviation, fully understand the effects on aircraft electronics in particular, but also have better things of dealing with the radiation doses for passengers and aircrew. But also, as was shown in 2015, we do need to keep reminding people that the sun messes up radars. And that many of you will know there was a famous incident in Northern Europe where in Belgium, Estonia, and Sweden, there were lots of false echoes in radar systems, aircraft radar systems, because of a solar radio burst, and that actually caused the system in Sweden to shut down. This should be known. We've known about solar interference with radars since 1942. But in this case, it had been missed. So there's an issue about maintaining awareness of space weather effects, and that somebody doesn't design something that's actually vulnerable. Now, a big thing also in the moment to these days is also resilient position and navigation timing technologies, often just abbreviated to PNT. Satellite navigation has become ubiquitous, but we know it's vulnerable to all sorts of problems. There are plenty of space weather problems, both the solar interference with the signal during a radio burst, with TEC, the total electron content in the ionosphere, can change the delay, so it makes GPS harder to use for accurate position measurements. Also, scintillation in the ionosphere can actually disrupt the GNSS signal so that it's not actually received on the ground, so you lose the surface, and so on. And there's also plenty of other things that can do it, interference from other devices. If you're on a train, you've got tunnels and trees can get in the way, as a railway engineer pointed out to me once. So there's a lot of interest in developing robust precision navigation technologies that actually overcome both these natural hazards and, of course, people wanting to deliberately mess it up. And I love this slide this image I found yesterday, which shows the GPS satellites being blocked by interference in the ionosphere, and you might need to use another technology. In this case, they're suggesting the so-called eLORAN system, the enhanced LORAN. LORAN's a low frequency technology. I think that's correct. I don't think it's quite sickeningly VLF, around 180 kilohertz, 200 kilohertz that can be used. It's a derivation of radio technologies that go back to the Second World War, but a modern version that's much more robust. And so, that certainly is a potential alternative. And there are many other things. People are trying to look at a mixture of technologies. And then there's a question of to what extent is eLORAN might have vulnerabilities because of changes in the D region of the ionosphere might have traditionally affected that technology. We think eLORAN's more robust, but it needs to be checked out. Lastly, last thing in the whole set of slides, is I come back to the interconnects. The UK has a lot of interconnects for electricity. We have the 3 lines down in the lower right, lines to France, which I think, in fact, there are 2 to France, the line to Belgium and the line to Netherlands. In the middle, you've got the line between Wales and Ireland. You've also got an internal line shown in orange running between the west of Scotland and the northwest of England. But in green, you've got the link between Northern Ireland and Scotland. And then on the left, you've got the interconnects that are now being built from Britain to Norway and Britain to Denmark. And also convenient because that dot points to the Shetland. I think there's also plans for a link to Shetland so that we could have wind farms in Shetland feeding power down into Scotland. And in the future, we might have might finally manage to make the economic case to have a link to Iceland so we can tap into geothermal power. So we need to understand better how all those things work. I mentioned before that these are the high voltage DC lines, so they probably block the GICs, but we need to look more broadly. Are there any issues there? And also what happens if something goes wrong at the other end or something goes wrong at our end when we're trying to supply power. At the right hand, we have the words North Sea, and so quite a bit of this is going to be about exploiting the wind power potential in the North Sea, which is an enormous resource and not one to be ignored.
What does it mean? Are we not going to have fun?
Okay, I think that's about enough I really want to say.
Yeah, we are. We're already doing it.
So thank you, Mike.
Okay, I wanted to finish on this future view rather than give a summary.
Yeah, that's no problem. We've got a few questions that have come up. We've also got Clive with his hand up. But Clive, I'm going to come back to you in a couple of moments. Ewan Haggerty, it's easier if you come in on your questions. You had 2 long, comprehensive comments and questions in there. So Ewan, if you can unmute yourself, please, and come in.
Hello there, can you hear me on this bad machine?
Yeah, I can hear you fine, Ewan.
Okay, Mike, but that breakdown that you presented with all of the systemic effects and showing the complexity of them was a very useful diagram, which Krista Hammond and myself from the MOSWOC have been using as a kind of a basis for a space weather toolkit. Now, the thinking that we've been having is that whilst it's very useful to have these illustrative scenarios which show what can happen in an extreme space weather event and all the complexity, for training purposes, you might not want everything that's on that menu. And also it might not be possible for you to arrange the training delivery that you wish to have to fit exactly with the scenario which has been pre-developed. So the danger there is that you wind up with a very good scenario being inappropriately applied and kind of breaking the laws of physics, which leads to counter training and people picking up on the wrong inferences from effects. So I just would like to ask, what's your view on how to train people for space weather events, and how can you check that the training is actually having the intended effect? Because it seems to be quite difficult.
I think what the simplest thing I would say is keep talking. That you really need dialogue. You can train people, but then talk with people, and actually see what they've taken on board. One of my oldest colleagues said to me, rather more decades ago than I wish to remember now, actually, we learn by osmosis. So it's not necessarily the first time or even the second time. We just have to keep going around it until some of these facts settle in our heads. And I don't think there's really too much substitute for persistence in terms of keep talking about it and explain something, see how people respond. I'm trying to see what to say other than that. It's not a neat answer, but I suspect you know that. I'm trying to think, sometimes when we've done training exercises, or at least done exercise with people, you'll suddenly in the middle of the conversation, you can pull out things. You suddenly realize somebody really doesn't get it. And so then you can try and highlight some of the issues that they need to address.
Yeah, I think the point that we've been addressing is that if you have a overly simplistic scenario and you have event A, then event B, then event C, then it tends to sink in and that becomes the remembered fact. Whereas it might be equally possible for you to have another space weather event where that sequence of effects doesn't happen, and to believe that it would and to react that way actually means you're doing more harm than good.
Yeah.
So
it kind of links in with when we've discussed with folks in government about why the SAGE system in the UK is meant to work with that, is that you have some general ideas about what could happen, but the principle of the SAGEs is that in government is that they're a dynamic body that's responding to the actual emergency and can customize to that emergency and don't stick to some pre-planned perception of what the emergency is going to be. When I've spoken to contingency officials in government, they've always been very strong on that they realize that you can over-plan, over-train, in the sense that people then come to emergency with a preset idea of how the emergency is going to pan out, and it may be something completely different.
Okay, that's an interesting comment. One of the scenarios we had in mind was that you're going to be in receipt of some severe space weather, and one of the first things that is going to be affected is your capacity to communicate effectively. And also, it's likely that although we've got some really good forecasting capabilities, the forecasts and notifications have got their own problems in of the times of generation and what the confidence levels are for action. So going along those lines, it's reasonable to expect that people who have an active role to play in dealing with an emergency might have to operate autonomously to an extent, or from an interpretation of the material they're receiving. So I was just trying to come up with a way of giving a good example of how, or a good training experience, so that people would be able to confidently do that and get it right most of the time.
I think there's no substitute for trying to at least pull out to get people to understand the main differentiations, particularly the differences between the radiation storms and the geomagnetic effects and the different drivers, so that they know these can happen at subtly different times. And it's also understanding how some effects build up. Like I say, satellite drag is something that for a low Earth orbit, satellites will build up across the storm, creates a storm. So where you've got a long-lived but moderately high storm, it can produce quite large drag effects, even compared to a short, sharp storm. So different storms have different characteristics. There's no real substitute for trying to raise awareness, is there?
No, not really. It's just but trying to come up with a mechanism by which you can build up a good level of awareness and a good level of insight into how other people that you have to deal with are also affected at the same time.
Yeah, I'm not sure much else I can say there other than keep talking, dialogue, isn't it? Yeah, well, there's no substitute for that. But it's also, I think, it behoves those of us who are experts to watch out for when we see misunderstandings emerging and tactfully try to correct them. I can think of some examples, but maybe I shouldn't cite them as that's going to expose. Yeah. But yeah, particularly the geomagnetic storm versus radiation storm is a big issue to highlight, and I think one can do that fairly tactfully.
Okay,
Thank you, Ewan.
Thank you, Mike. Thanks, Mario.
No problem. Clive, I will come back to you. There's a couple of things I want to circle around first. Mike, there's a couple of comments in the chat. First one is Edmund Henley, again, Met Office, noting that as well as GNSS even, too many S's, they've speculated internally in terms of flagging GLE risk to autonomous navigation, and there's some colleagues starting to work on that. They're unsure as to whether it will be likely an issue in the future or whether there's any companies involved in planning radiation hardships. That kind of comes about some of the comments you made, Mike. And secondly, from Mike Marsh, also Met Office, that the other emerging innovation is about electric charging vehicles and the new vulnerabilities perhaps on the grid of implementing the vehicle charging points. So they're just related comments, I think, on some of the things you mentioned. I don't know if you want to expand on any of that.
I can expand particularly on the GLE issue. Certainly, people have been worried about single event effects in automotive electronics for the best part of the last 20 years. And it's been, it's constantly being flagged. The car companies really have no excuse not to know that this issue exists, and that they need to write robust software that can deal with safety issues. As I've whinged about to you on occasions, and I've even written about it, there is ample evidence that in the past that some of the car companies have not been up to speed on this, and hopefully they are now better. The Toyota accelerator scandal exposed the fact that the software was not being written in a safety critical manner. It handles the safety critical issues. There's also the whole issue with the emissions scam test. Makes you wonder about some of their software development too. Hopefully the industry is now doing a better job. You can write software well to deal with safety critical issues. Your most obvious thing is you have these error correction codes that scan memory can look for where a single bit has changed and locate it and fix it. If the events don't happen too fast, then that's fine. You can fix that. And I think that's probably standard on a lot of space missions. Probably, and I would certainly hope so in aircraft applications. It's very easy to cope with modest levels of single event upsets with the right software. Yeah, but it's all. But the thing of that, it's all part of making driverless cars safe.
Yeah, I agree.
Yeah, and there's a whole issue of technology there, but there are, I think, a lot of good people looking at that who know what they're doing.
There's three little points I'll bring up, and it might lead back to something that I think Clive may come in on. So thanks again, Clive, for being patient. Henry Dodds just raised the fact that the National Risk Register framework timeline used to be 5 years. And in 2020, they seem to have reduced that down to 1 year now. So perhaps there'll be more common updates there. But David Alexander raised a question about whether or not we've worked with the new UK Space Command in terms of these reasonable worst case scenarios.
Not yet. I suppose it's a simple answer, but we hope to. We hope there will be some. But generally, we're focusing, I should say, most of our focus is on the civilian side, but particularly Met Office is will be is just one of the ways we can interface with the military. They will certainly they are providing space weather support to the military, obviously, as they always have provided space weather support to the ordinary weather support to the military.
Yeah. Another question from David Alexander that came up a while ago was about the growth of Bitcoin and other cyber currencies. Is this growth worrying given the reliance on electronic mining?
I have sometimes thought I should sit down and try and understand what Bitcoin is about, and come to the conclusion I have better things to do with my time. Like making dinner and things. Okay. I really don't. I have not really got into Bitcoin enough to comment. It just seems weird to me. In a world where it's not real money in the sense that you can't pay taxes. Somebody said the real definition of money is what you can pay tax with.
Yeah.
And so Bitcoin is a bit weird that way.
Fair enough. And finally, a little while ago, Masha Kuznetsova commented about the spacecraft missions and different instruments having their own thresholds for radiation fluxes. And these levels might be different from different spacecraft, instrument, operator, etc. She's asking whether or not we know who's responsible to define those thresholds and how did that feed into the reasonable worst case scenarios?
I think the answer is it wouldn't. The reasonable worst case scenario is we're trying to define what the reasonable worst case environment might be. So that defines an environment and you might then need to modify that. If, for instance, a magnetospheric mission, you might be in a different place. If you were further from an antiplanetary mission further from the sun, you might want to vary the fluxes by the inverse square law from the sun. But it's ultimately down to the spacecraft designer. They want to build their spacecraft. Here is the environment. They then need to design to that. And typically they would want to know what, for a spacecraft, given its mission lifetime, what is the radiation exposure that would be less, my probability is the right way around, such that there's only a 5% chance of exceeding that radiation threshold during the time of the mission. That's typically kind of design criterion you go for. And then it's down to them to design the spacecraft. Do they need to put shielding in around things or whatever? And it's, for instance, we provide reasonable worst case scenarios. If somebody wants to survive a 100-year storm, we would do that. But if you just want it to last your design lifetime, you would use something like the European Cooperation on Space Standards has a space environment standard that I and some of those on this call have contributed to in the past.
Thanks, Mike. Clive, thank you for being patient. If you want to come in now, Clive.
Okay, I think I've unmuted. Yeah, I'd like to go back to the National Risk Register. I have some difficulties with it, to be perfectly honest. We occupy one box there, i.e. space weather, at the 1 in 100 years, and we've got a certain measure of the severity of that, which is maybe not unreasonable. It's a bit less than the 1 in 100 years pandemic, which is probably a fair comment at the moment, what we're suffering. But we've got a spectrum of events. We have 1 in 500 years, we have 1 in 1,000, we have 1 in 10,000. We now have on record at least 5 cosmogenic nuclide events well documented between about 660 BC and 1279 AD, running from 1 order of magnitude to a factor 30 worse than anything of the space age. Now, I think that would rather put space weather up into a different box. You could move it to the left and upwards without the chart in front of me. I can't remember what the terminologies were, but we do have worse than 1 in 100-year event, and we have spectrum of events and all hazards. It always seems a bit mistake to put everything in just one box.
Yeah, I think that what's in the box is the 100-year storm.
Yes, it is. And
I think, therefore, if we would really need to look a bit more harder at what is the one in the 1,000-year event that would be in one of the other boxes.
Yeah.
And we
Well,
have some idea in terms of radiation. We have absolutely no idea in terms of geomagnetic effects. Yeah, there are some old things in records which suggest, that at the same time as the 774 AD, that it was aurora over the south coast of England and things like that. But you've got to interpret the Anglo-Saxon Chronicle in certain ways. But
we do have the evidence for radiation. It's obviously naive to scale geomagnetic storms in an ionosphere quite the same way. But they could certainly be significantly worse. But 30 times in radiation is pretty damn serious, actually. So it should be borne in mind.
Yeah. And I think we're almost there. That's a challenge. We need to be able to model the generation of such events. To better understand what would be happening on the sun to generate such an intense event.
Yeah.
And that then might give us a clue to what it might do in terms of coronal mass ejections.
Yeah, we'd certainly have some pretty impressive sunspot area. So,
well, yes.
So we might stay on the ground and bury ourselves underground.
Well, sunspot area is roughly speaking a measure of the energy available to do something. Some people have put limits on size of events, but saying you'd need such an enormous sunspot. It would be so blatantly obvious it would be written down in records.
Yeah, we seem to see 1,000 times solar flares on sunlight stars when we search for extraterrestrial planets.
Yeah, we don't have many that are such slow rotators as the sun.
No. Anyway, I'll just say that the radiation is fairly definitive now. So 30 times for 1 in 1,000 years is not unreasonable.
Thank you, Clive. One slightly related comment about the risk register, Mike, is Bob has asked about whether or not the Earth's reversal magnetic field should be considered. Obviously not necessarily space weather, but whether or not that's something that should be considered for the future, if you have any comment on that.
There's certainly some work done in the SWIGS project, I think, at Leeds, looking at what would happen with those kind of evolutions and where would you, the naive thing is that if you got rid of this, the dipole died completely left with a quadrupole, we'd have an auroral zone around the equator. So the issue more there is that things might move. I think that the big issue there is do you have particular effects in different regions of the Earth where you wouldn't otherwise expect them? Most obviously is if you could actually have auroral effects at the equator. That's a big change.
Yeah, thanks, Mike.
But it's still very much in the research phase.
Okay, so we've come right to the end of our time. So thank you very much, Mike, and thank you everyone for all your questions and all the comments. There's still a good chat going on in the actual Zoom chat box. So once the recording is finished, I will leave the meeting open for a little while longer. But before that, I just want to remind everyone that this is day 1 of a 3-day mini series. And tomorrow will be the swimmer program overview. And on Friday will be UK space safety. So all I'm going to say is thank you again, Mike, and thank you all for attending. We had
and my thanks to everybody too.
We had over 100 people, unique participants in total, 96 at its peak. So that was pretty good going for the first day. So thank you, everyone. And if you just want to hang on till after the recording is stopped, and you can then carry on any informal discussion. Thank you, everyone, and goodbye.